So the rename operation is a bit separate, and it might seem more straightforward than it actually appears to be under the hood. And I wanted to have its own separate video just because there's a bit of algebra going on here too. But essentially, our rename operation, where we change our relation R from with attributes A, B into relation D with attributes A, D, is something along the lines of this behind the back end there. So this allows us to name and refer to results of RA expressions. We may want to do this if we have a very complex relationship that we got out of a RA expression and we want to refer to it again, or we actually want to refer to our relation during work, but we don't know which one to actually specify, so we can rename some operations there. So essentially here, when we say rename the relation R with our notation of X at the bottom here, and we have an arity of N, so this essentially means the number of attributes we have is N. This operation here is going to return the result of expression E under the name X, so essentially what is in here, and with the attributes renamed to A1, A2, up until AN. So essentially, what we could do back here is what I would say here is P of R is equal to AD. That's how I renamed the attributes there, okay? So the actual functional the algebra that we see here is the rename of relation R with expression X is equal to all the tuples inside of X itself, such that all the tuples are in R. So we just transferred them over. If we said the rename of relation R with the expression X with the attributes A there is such that all the tuples in X and their attributes are renamed here to whatever is provided in the relationship R that we first started with, okay? This might be a little convoluted looking, and maybe the vocalizing it might be a little confusing too. But essentially, what we're trying to do here is just go ahead and shift the attributes that we currently have into new ones that we might need. Cool. So we could see here, one more thing that might be a little hidden that I didn't say earlier as well, is that when I do my P of R operation, my X in this scenario is going to be the new relation that I get, right? This D is creating this new relation D down here with the attributes of A and D provided, okay? So that's essentially how this works for us there. And again, if I put C and D here, what I would get is a relation D with C and D provided. So essentially, when we're asking questions, where is the A and the D from for us? We have our A from R and our D from S over here. And if we actually look at the middle of our code here, we see the rename of relation S using this attribute D in here. We'll rename it there. Get the Cartesian product of that renamed relation times it by relation R. From this relation outcome, go ahead and select where the A is equal to D dot C from here. And then go ahead and project our A and D dot D from that relationship outcome there, okay? So we can get very, our operations can become very complex that we're looking at too, but this is just one way to look at the rename operation. Whenever we're doing this in code, it won't be as intense as this one, but it's useful as well. One more thing here is these operations, rename is kind of useful because we could use it in any way that we'd like. We could use an alias such as the arrow over instead of having to use P in this sense here. And we could also use positional notation. And again, if you can think back to Python and some other languages where you do the format.print and where you put your variables inside of that, the position of them can help with that. So essentially, if I say project $4 from the Cartesian product of instructor and instructor, I can use a positional argument. So this $4 is actually referencing this relation. This $8 is referencing the second relation here for the second instructor, okay? Again, we're using instructor twice, so you can do a Cartesian product of yourself as well. But this is just useful too in case you want to go through it. Cool. So there's a lot of formal definitions here that we can look at as well for each of these. I won't go through all of these here because we got through them earlier, but essentially take a look at these. This is kind of what you're doing when you're doing this high level SQL code and you're typing in select star from table. This is kind of what's going on in your background there. Okay. So just get a little familiar with these aspects. I broke it into the binary, unary parts for us. But again, if you have any problems with the calculus behind it too, just let me know. So the next few slides here, including on the PowerPoint, are some example queries. The PowerPoint does a good job of going through all of them, but I'll just go through the first one here. So if we find all the instructors in the physics department, along with the course ID of all the courses they have taught, right? So our first query here is going into the middle. So we go ahead and we can do a Cartesian product, get me all the instructor and teachers, composable of them there. And then what we're going to say is select where instructor ID is equal to teachers.id. These are our tables or relations from there too. Furthermore, select the department name where it's equal to physics, and then project me their ID and then the course ID from each of these as well. Okay, so this is kind of how we can build out these queries. And we can see there's a few queries here. And then for the PowerPoint, it asks you to go through which ones are equivalent as well. Just make sure that when you're actually running the code later on when we do these examples, it's useful to, as we see here, swap these around just to see what the difference are. Okay, so the rest of these have example queries, but essentially we're going to come up with more of these as we go through. And I think once we actually get into the coding, it'll be useful. But this is just to provide you with a broad overview of the calculus behind these operations and why we use these certain codes for them.